All right, so we are back here talking about pressure and fluid statics, and in this video I want to work an example problem where we look at the pressure force that is generated on an arbitrary shape on an inclined plane. I had previously done a simpler example, and we've gone through and developed some theory on how to analyze these, and key ideas being that the centroid is, if we can figure out where the centroid is, the depth below the surface of that is the average pressure across, the pressure at the center is the average pressure across the region. So we can multiply the area by the depth of the centroid and the specific weight to get the average pressure force on that shape. And then the center of pressure is below that. And then to figure out where that is, we have to do a little bit of a moment analysis on an inclined plane. And if we do that one, we can determine that it's a little bit below the centroid, which we can determine for a given shape using its moment of inertia and, again, the area and the location of the centroid. And so there's a procedure that we can use here to follow this kind of problem. And I did an example previously where it was not a flat plane for a rectangle. And this one I'm going to do a little bit more difficult problem, I think. And so again, the first step is to find all the formulas. You need a table for the shapes that you're looking at that you can use, and I have provided that for students in my class, and you can find them easily online for formulas for the location of the centroid, the moment of inertia, and then the area of the shape that you're looking at. So you need that first. Then you have to look at the geometry of the region and figure out where the centroid is relative to the water surface. Okay, so the part one doesn't tell you anything about where this shape is located below the water. It just tells you something about the geometry of that shape. And then once we've figured out where that depth is, we can then get the magnitude of the force and figure out the location of the center of pressure using the parallel axis theorem. So we'll be going through this example here on this one for this trapezoid shape here. And it's the same for any region, and ideally you'd have a table that you can use to look up the centroid moment of inertia. And so here we have this trapezoidal shape, and it's tilted. We said this is a 60-degree angle here from the vertical. And again, what we're trying to figure out here, I use Z in these kinds of problems at least to refer to the distance below the water surface, and then I use Y as the distance along the inclined plane. So if it's a flat plane, Z and Y are the same, and that was what we did in the last one. Here it's actually inclined, so this is a bit harder. Anyway, the centroid's right here in the middle. If it's a rectangle or a shape that's symmetric. Now, because it's a trapezoid, it won't be right in the middle. We have to figure that out. And then the center of pressure is a little bit below that centroid. All right, so let's draw. So I went to my supplemental file, and I'm just going to copy the information that I found here. So we're looking at a trapezoid, and the shape looks like this in the file that I am looking at. And so there's some centroid here, which is Y bar. So I'm going to call Y bar the location of the centroid relative to the bottom of the shape. Okay, so this is like Y bar, Y equals 0 here in this little world. That's different than the Y over here. This is in the context of this larger problem. This is just looking at a trapezoid. Okay, so Y bar is there, and then we're in the supplemental table that I looked at, it lists the height and then the top and bottom width of the trapezoid here. And then I have formulas here. So the first thing that we do is, given the top and bottom width of this trapezoid and its height, we have formulas that we can use to compute the area, the location of the centroid in its little geometry world, and the moment of inertia. And so those formulas for this shape in my table are A is equal, or big area, A is A plus B times H over 2. So this is really just the average of A and B times H, which should be intuitive. I think it's intuitive. So 5 plus 3 times 2 over 2 gives us 8 square feet for the area of this shape. The location of the centroid Y bar in a trapezoid. So for a rectangle or a circle, something symmetric, it's usually pretty easy to figure out where the middle is. When it's not symmetric like this, it's harder. And so the formula for this shape is H times 2A plus B over 3 times A plus B. If you don't have a center if you don't have a file that you can use for the geometry, then you will have to derive this with some calculus. And again, that's the sort of thing you might do in like a statics class, but we're not going to do any of that here in the interest of time. Okay, so we have h is 2, and then 2 times a is 5. Oh, right. So for our shape here, sorry, I didn't copy that down. I should have put that over here. But we have a is equal to 5, b is equal to 3, and these are in feet, and then h is equal to 2 feet. And then we're also going to need to know the specific weight of water. So here we're working in feet, so I used 62.4 pounds per cubic foot. The density of water at 4 Celsius in pounds comes out to 62.4 pounds force per cubic foot. So we'll need that later in this calculation. So anyway, sorry, going back over here to the centroid, it has A and B, and so I needed to clarify what those were. So 2 times 5 plus 3, and then over 3 times 5 plus 3. And those are all in feet, and so we will get an answer there that is in feet. Okay, so 1.08 feet is the location of the centroid. And again, this is the height here above the base of the trapezoid. If you look at the diagram, okay, this height here is y bar above the base, 1.08 feet. Okay, for our shape. And then last we need the moment of inertia, and so the formula is for trapezoid, it's h cubed times a squared plus 4ab plus b squared. And all of those are in parentheses. So h cubed, a squared, 4ab plus b squared. This is again a formula that comes from a table that has been derived for this shape, given a, b, and h as they are defined here. And that's the top, and then that's divided by 36 times a plus b. So we can plug in the numbers here. So 2 cubed for h. A is 5 squared plus 4 times 5 times 3 plus b squared, which is 3 squared. Okay, that's the top, and then the bottom is 36 times 5 plus 3, and that comes out to be 2.61 feet to the 4th power. 2.61 feet to the 4th power. Okay, so now we have the area, the location of the centroid in the geometry of that shape, and then the moment of inertia. And so the next thing that we need to do is step 2 in our process to figure out where the centroid is relative to the water surface. All right, so we have this handy diagram here that we can use to think about this. And so here in our problem statement, we're told the top of this trapezoid is 5 feet below the water surface. And so that means that the location here of the centroid is going to, we have to go a little bit further down to get there. So it's going to be 5 plus the location of this centroid tilted down. Okay, and so we have to do a little bit of geometry. So for this angle here, the sine of, if we multiply a length along this plane by the sine of 60, it will tell us the length along this plane, and that's what we need to know here to see how far down below the surface this is. Okay, and so we also have that it's 1.08 feet from the base of it up here to the middle if we're looking at it straight on. But so if it's tilted, it's going to be something a little bit different. And so we can then from that determine that the depth of the centroid ZC is going to be 5 plus this distance here, which is going to be, it's a height of 2 minus the 1.08. There, that's going to be this distance, and then we need to multiply that by sine of 60. So 2 minus 1.08 times sine of 60 degrees. And if I multiply that out, I get that it is 5.79 feet below the surface of the water. Okay, so that's step 2 in our 5-step process. And then to get the resultant force now, it's just a matter of doing a little bit of plug and chug here. gamma times ZC times A, and so gamma is 62.4 pounds per cubic foot, and ZC is, we just determined that it was 5.79 feet, and then the area up here we determined was 8 square feet, and so that all multiplies out nicely. Don't have to do any extra unit conversions, and I get that that is 2887 pounds. Okay, so that's the magnitude of the force, which is one of the things we need. And now we need to figure out where exactly that acts. Again, now we know the location of the centroid, but we know the depth of the center of pressure is a little bit lower than that. So in order to determine that, let's see, we need to know the distance here. Okay, our formula here to determine the centroid requires us to know the distance along the tilted plane. So again, if it's straight up and down, y and z are the same, and we would know that yc was zc. But here, because it's tilted, we then have to do a little bit of geometry again, or trigonometry, I guess. And so it's got to be the 5.79 and then divided by the sine of 60 to give us the length along this plane. So we'll say yc is equal to zc over the sine of theta, and here that's 5.79 divided by the sine of 60 degrees feet, and I get that that is 6.69 feet. Okay, so that is the location of the centroid here along the y-axis, and then we can plug in our formula here to get the location of the center of pressure here. Yp is equal to Yc plus I0 over A times Yc, and so plug and chug, 6.69 plus 2.61 over 8 times Yc was 6.69, and all those are in feet, so we don't need to write out the units, and we get 6.74 feet. Okay, so again, this is not very much different than the location of the center of pressure, but it is always a little bit lower. And again, the difference between these two gets small if something is submerged really deep, but in this case it's not very, or it's kind of deep, so there is a difference, but it's not huge. We might also be curious where this point is along the, straight from the surface. So this 6.74 is the distance along this plane. If we wanted to know z, the depth there, we can also figure that out. Zp, again using trigonometry, is going to be 6.74 over the sine of 60 degrees, and that comes out to it's times 60, not multiplied. It should be times the sine of 60 degrees, and that gives us 5.83 feet. Okay, yeah, because the distance this way should be less than the distance on that tilted plane. Sorry, you need to multiply by sine of 60. Okay.